Welcome everybody to section 8.3, the number e. So in this section we're going to be learning about something called the number e, and we're going to use it in several ways. So we're going to be doing exponent properties with e, we're going to be graphing it, and we're going to use e in a compound interest formula that I'll show you later. To start off with, let's do a quick warm-up. I'd like you to pause the video and try these warm-up questions and see what you can do with this. Okay, if you have unpaused, let's check your answers. Add the exponents when I'm multiplying. Here I'm taking a cubed root and I end up with 3x cubed y to the fourth. Here I end up with 27x to the negative 6, and remember, 27 has its own exponent, so that does not move to the bottom, only the x to the 6 does. And last but not least, for this problem, when we simplify, we end up with 1 over 3x. Alright, I want to show you the number e. So I'm going to show you something right now. This is optional to write down. You can just watch if you want to. So I want to show you something here. So let's say I was trying to do an exponential problem, and I'm starting off with 1 plus 1/10 to the 10th power, and I'm going to figure out what that is, and I end up with the number 2.594. Okay, I'm going to do it again. This time I'm going to have the bottom number be 100. And quick note, this is from that formula we learned the other day, the interest formula where you're compounding and then the n is on bottom and the n is the exponent as well. Alright, so when I solve this, I end up with 2.705. Let's go again. I'm going to now make n 3000, and this is leading somewhere in case you're wondering. Alright, and basically what I'm trying to show you is, and I'm going to stop there, but basically, as n gets bigger and bigger and bigger, as n gets bigger, this answer approaches the number e. And as this gets bigger and bigger and bigger, it approaches the number e, which is 2.71828 ... E is a number just like pi. You know how pi on your calculator is 3.14 something 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 something? E is a number like that. So mathematicians, well, you personally might not use it in your life, but if you go into finance, it's used all the time in different formulas. So instead of people having to type out that number every time, they've just made a symbol on our calculator. Here, if you look at your graphing calculator right now, I can show you where it is. It's actually on your calculator in two places. So first of all, E is the shift key of the divide by symbol. Look at your calculator. E is the shift key of the divide by symbol, and if you just type that in and hit enter, your calculator will show you 2.71828 something something something. The second place E is on your calculator. On the left side of your calculator, kind of near the on button, there's a ln key, and it says e to the x. There they have made for you a e with a pre-typed in exponent, so that if you're trying to do e to some exponent, it just makes it slightly faster, milliseconds faster, but so that we'll use later. Alright, now to start off with, we're going to just be using e with some different exponent properties that we actually learned in Chapter 7. So this part is actually just a review from Chapter 7, but what you need to know is e acts just like an x. And we're not actually going to type this into our calculator and find a number, we're just going to try to simplify right now. So if I look at this first problem, I'm going to use the same exponent properties we already learned. So e cubed times e to the fourth. Remember, you add the exponents. The final answer is e to the seventh. Remember, when in doubt, write it out. I got 3 e's times 4 e's, that's why it's e to the seventh. Alright, and now they're going to make things a little bit more complicated for you. So I want to show you, to start off with here, I look at my 3, and 3 has nobody to combine with, so I know that's just going to be there. But now look at your e's. So remember, we can take the top exponent, subtract the bottom exponent, and we can still do that even if there's x's there. So e to the 2x minus 1x, and so e to the x is the answer, and that's positive, so that stays on top. Next example. For my numbers, 10 divided by 5 is 2, and for my e's, e cubed divided by e squared, I'm in my mind thinking 3 subtract 2, which is a positive 1. That's positive, so it just stays there, and I don't have to write the 1. I could just put that down. All right, next. This, again, looks kind of weird, but remember, if I have two things multiplied together like that, you add the exponent. So I've got 2x plus 3x minus 1. 2x plus 3x is 5x, and that's all I can do with that problem. We could split it up. All right, let me tell you something quick. This, if you have that as your final answer, I will accept it, but technically I guess we could split it up like this, and then that would become e to the 5x divided by e. So if this was a more advanced class, I'd be forcing you to do that, but for this class, if you leave it like that, that is sufficient. All right. Fifth, I've got 2 times e to the negative 4th to the negative 1 exponent. First of all, I'm thinking distribute. Because it's multiply, it's allowable to distribute the exponent. Negative 4 times negative 1 is 4. And here, e to the 4th stays on top, while the 2 to the negative 1st moves to the bottom because of the negative exponent. Last but not least, I'm going to again distribute my exponent, so I have 3 squared, and then remember, I didn't mention this before, I'm assuming you remember, but when I say distribute, it's a power to a power, so I multiply them. So negative 4x times 2 would be negative 8x. And now I have a negative exponent, so 3 squared, which is 9, stays on top, but the e to the 8x goes to the bottom. Now this part, we're definitely going to have to practice more in class. So that part we will practice more in class. The rest of this section is all about graphing and using some formulas. So the rest of the section is going to be very similar to what we did in section 8.1 and 8.2. Okay, so a natural base exponential function, and by the way, I didn't even say this earlier, let me scroll back up. The number e, that is called the natural base. That is called the natural base. So if something in your book talks about the natural base, they're talking about the number e. We're going to make a general formula like we did when we were doing 8.1 and 8.2. So here I've got a times e to the x power. That's kind of my general formula. And it's similar to what we did before in that that is still the y-intercept. And also, I'm going to right away tell you, we're going to be doing up, down, right, left with this like we did before, and same rules apply as we did in 8.1 and 8.2. So if I do have a translation in the exponent, a plus moves it left and a minus moves it right, and outside of the exponent, a plus moves it up and a minus moves it down. And now we're going to actually, to graph it, use the same step-by-step we did the other day. So step 1, find the y-intercept and plot it. Step 2, find another point. And I'll show you in a second, it might seem weird, but we actually can just plug in 1 still and find a number. So I still recommend using 1 just because it's fastest, but you could use anything you want to. But I recommend you use 1 for x and then go ahead and find y with your calculator. All right, and we're only graphing those 2 points. So again, we're going to graph 2 points and draw in the shape. So let me just show you a graph before I have any numbers or anything. So I'm going to show you y equals e to the x and y equals e to the negative x. All right, so first thing I want to point out is because e is going to always be e. So in section 8.1 and 8.2, do you remember how the b value determined if it was growth or decay? That's not going to happen here because e is always going to be e, 2.718. So it's always going to be greater than 1. It's going to be the same thing every time. The thing that determines if it's growth or decay is the variable. So if the variable is positive, it is growth. And if the variable is negative, it's going to be decay. And I'm going to do, that's why I chose these two, because I want to do one of each type. All right, so, and these are kind of like a quote parent function if you want to think about that, but all of our graphs are going to look very similar to these. So I'm going to follow my step-by-step. Step 1, find my y-intercept. There is no a value, so I'm thinking it's 1 times that. So my y-intercept is 0, 1. Step 2, I'm going to find my other point. And my other point, I'm going to again use an x value of 1 just because it's fast. And I'm going to, just like we did in 8.1 and 8.2, I'm going to plug in that variable. And then this is where I'm going to type this in my calculator. So your choice which E button you use. A reminder again, if you want to use the E that already has the exponent preloaded, on the bottom left side of your calculator, it's the shift key for the LN button. It's the shift key for the LN button, and it looks like this. So in my calculator, what I would type in, it'll look like this. And that's just e to the first power, which is just e. So that's going to end up being 2.718. And because of the e being a decimal, all of these are going to be approximate for the other point today. All right, so 1, 2.7, there it is. I'm going to now draw in my general shape. And this one looks like exponential growth. And then I'm going to find the domain and range and the asymptote. Okay, so this one has the same asymptote as a normal exponential growth function. So the asymptote is at y equals 0. And the domain and range, the domain is all reals. So, you know, you need to know that an E graph, it is an exponential graph, just like we did in 8.1 and 8.2. It just happens to always have a base of 2.7182. But it is an exponential graph, so kind of same rules apply. So the domain is still all reals, and the range, I'm looking at where my graph is. I know it's going to be values greater than 0 if I see my whole graph is above that asymptote there. So I'm going to say y is greater than 0 for the range. All right, for decay, this has as well a 1 for the a value. So my y-intercept is 1. And then to find my other point, I'm going to plug in a 1 again for x. And so in my calculator this time, it's e to the negative 1 power. E to the negative 1 power. And that ends up being 0.4 if you round it. So 1, 0.4. And so my graph looks something like this. See how it looks like decay? And the asymptote hasn't moved. That's at y equals 0. And the domain and range are actually the same. So the domain is still all reals. And for the range, it is still, even though it's going the other way, all the y values are still above 0. That's what we're looking for. So y is greater than 0 still for my range. All right, so let's quickly talk about growth or decay. And I know on here I said to find the y-intercept and find one other point, but we're actually going to do that 4 more times on the other side, so we're not going to do that step. I just want to say growth or decay. So based off of what I just said, go through quickly and pencil it in, pause, pencil it in. What do you think for each of them? All right, let's check your work. Decay, growth, decay, and see how it doesn't matter what's in front of it. All that matters is the exponent, and this is growth. So even though there's a negative 3 in front of there, that doesn't make it a decay function. It will make the graph a little different. If you have that negative in front, it does flip over the x-axis, but it's still considered a growth function, because remember from the other day, my growth could look like that, or if I just took that same exact graph and mirrored it down this way, both of those are considered growth. So this one with the negative in front would look like that, but it's still considered growth. I know it's kind of weird. All right, go ahead and stop the video, and I'll meet you with part 2 on the back side. Thanks.